Boa noite a todos, bem-vindos a mais um Tech Tuesday, um evento aí promovido, né, pela SPE Brasil, né, que é uma seção, né, da Society of Petroleum Engineers, né, órgão internacional, né, na Associação de Engenheiros de Petróleo, tá bom? Bem-vindo a todos. Meu nome é José Sérgio, eu sou o diretor de eventos, né, do capítulo da SPE Brasil, estou hoje aqui representando o nosso presidente, né, o Pedroso, que não pôde comparecer, mas é com grande prazer, né, que eu faço a abertura, e vou falar um pouquinho dos próximos eventos, né, que a sessão está promovendo, né, tanto o SPE Brasil quanto o SPE Internacional, né. Os próximos eventos, né, como a gente vê no próximo slide, a gente tem uma série de eventos, né, previstos, né, por ano de 2023, não vou detalhar cada um deles, né, mas a gente, como uma organização que trata de engenharia de petróleo, a gente tem eventos aí dos mais diversos assuntos, né, que são de interesse, né, da indústria nacional e internacional, passando aí, né, por workshops relacionados a campos maduros, descomissionamento, integridade de poços, segurança operacional, workshops de transformação digital, descomissionamento de poços, né, nesse caso esse evento aqui em parceria com o evento da SPE Internacional, eventos de sustentabilidade, como o simpósio de sustentabilidade do SPE Brasil, o Brasil Onshore e o SPE Brasil Subsea Symposium. Tá? Então, esses são os eventos que a gente está programado, né, para esse ano. Tá? Agora, mais recente, né, agora no dia 24 de maio, né, a gente vai ter uma edição do SP Energy Talks Brasil. Tá? Nessa apresentação, a gente vai falar, né, vai ter convidados como Paulo Prunzer, que é engenheiro master da Petrobras, que vai palestrar para a gente sobre hidrogênio, né, estado da arte e desafios. Tá? Então, esse evento vai acontecer aqui no nosso canal YouTube. A gente vai ter, moderando essa apresentação, a Gilcélia Borges, né, que é engenheira sênior da Petrobras. Então, é um evento muito importante, tratando de um tema muito atual, né, para a indústria de energia como um todo. Né? O próximo workshop, né, que nós temos, né, agora no dia 30 e 31 de maio, é o workshop de campos maduros offshore. Tá? Esse evento ele visa discutir as perspectivas do campos maduros offshore, né, do Brasil. Tá? Então a gente vai ter participação de importantes empresas, a gente tem como patrocinadores a Petrobras, o governo federal e outras empresas. Tá? Vai ter muita gente boa, muita gente, tanto no âmbito gerencial quanto técnico, participando, né, e discutindo, né, os nossos projetos, né, e o futuro, né, desses campos maduros que ainda tem muito, né, valor a gerar, né, para as empresas e para a nossa sociedade. Né. Pode passar, Eduardo. O próximo evento internacional que nós temos, dia 14 e 15 de junho ainda desse ano, é o SPE Latin American and Caribbean Petroleum Engineering Conference. Tá? Então, nesse evento, que vai acontecer em Port of Spain, Trinidad e Tobago, a gente vai ter uma série de sessões técnicas, né, e o encontro de diversos especialistas, né, dos mais diversos temas, né, e áreas da indústria. Né? Então, é um evento muito interessante, né, que realmente vale a pena, né, a participação. Ok? Pode passar, Eduardo. Aqui no âmbito do SPE Brasil, né, a gente vai ter o simpósio de descomissionamento. Tá? Esse simpósio ele vai acontecer logo mês que vem, dia 27 e 29 de junho, tá? No Windsor Guanabara Hotel, aqui no Rio de Janeiro. A gente já está com as inscrições abertas, já temos, né, vários inscritos. Aqui a gente também vai ter a participação de diversas empresas, a gente vai discutir aspectos de negócio, aspectos regulatórios, né? Então, é um tema também bastante atual, e um tema que vai permanecer aí, né, em destaque na indústria por bastante tempo. Tá? Então, eu convido vocês também a se inscreverem e participarem, né, desse evento. Tá bom? Pode passar, Eduardo. Bom, agora, né, com grande prazer, né, que a gente anuncia oficialmente a nossa Tech Tuesday, né, do dia 9 de maio, né, de 2023, onde a gente vai falar sobre Gorgon, né, sobre captura, né, de CO2, né, storage de CO2, ou Carbon Capture and Storage, e são lições aprendidas, né, desse projeto, desse importante projeto de CCS. Né. Para poder moderar, né, comigo, né, essa apresentação, eu vou convidar aqui o Pierre Edward, né, que é o nosso diretor de Relações Internacionais. Né. Pierre, por favor, né, bem-vindo aí, né, pode se apresentar e dar início aí à nossa Tech Tuesday.
Good evening to everyone joining the call today or joining after the fact, also in replay. So a few words about the event and a few words about me to begin with. So I'm French. I currently with Trident in Brazil, and I was asked by SPE to provide some help with developing international relations. So my expertise today is really about, I'm a mechanical engineer by background. It's really more about well construction, but I have a curious mind, so I'm always interested in finding more aspects, discovering new aspects of engineering. So a few words about SPE. So thanks to SPE for putting forward this kind of event, and it's really about shared expertise, resources, and lifelong learning opportunities to fuel the success of our members and the future of our industry. With no further ado, I'll quickly jump to a short bio about our guest speaker today, Matthew Healy, whom I had already met previously during another SP event, is the managing director of PACE CCS, present in London, Houston, and Kuala Lumpur. PACE CCS is a leading consultancy in the design of CCS infrastructure with experience with more than 50 projects across the world. Matt is also a member of ISO TC 265, responsible for development of standards related to carbon dioxide capture, transportation, and geological storage. Mike, my pleasure. Over to you.
Thank you, Pierre, and thank you, Sergio, for the introduction as well. I'll just start by saying thanks to the SPE for this opportunity to talk. I'm sitting in a hotel lobby in Houston this evening, where I'm here working with our team in the USA. I'm based in the London office, although those of you with an ear for the accents might be able to hear a bit of Australian in mine, which is where I'm from originally. And I guess, Sergio, yeah, well, there we go. There's the slides, look at that, like magic. And I'll get right into the presentation. And I look forward to questions as we come to the end. I want to talk about the Gorgon CCS project. CCS is a new industry, as we all know. We're obviously involved with the industry around the world. And I do think because it's a new industry, it's very important that we share information. And the fact is that we often learn more from projects that went wrong than projects that went right. And so my goal here is to share some of the lessons from Gorgon and talk about what that means for CCS projects in general. A quick introduction to PACE. Pierre has given us a quick introduction already. We're a multidisciplinary engineering design consultancy. We specialize in CCS. We're a relatively young company. CCS is a relatively new industry, but we have got a very broad footprint across that industry. We're working on around about 25% of the CCS projects globally. So since that bio was written that Pierre gave that said we've worked on over 50 projects, I can now say that's over 70. And we've got a very good idea about what's going on at the moment in the CCS world and what we can expect in the future. I'm on the ISO committee, as Pierre mentioned, which is responsible for standards related to CCS. And what that means is that when I talk to you, I can draw on the experience of the terrific ISO committee that there is, which is a truly global one. And I can take those lessons and bring them to you into this presentation. And I can also rely on the experience of my own team at PACE CCS. With that amount of experience that we have, there's obviously a lot of learned knowledge. And so I'm thankful to all of those people that I'm relying on to try and make myself look smart, which is hopefully what comes across here. Most of our work at PACE is in Europe, Asia, and the United States. I've just mentioned some projects here. In case there are projects of interest to anyone who's tuned in, if you have got any questions about any of these projects, I'd be happy to discuss in a question at the end of the presentation. Right, why Gorgon? So it's a major problem. It's a high-profile project. It was, and in fact still is, the largest operating CCS project in the world. They hoped to inject 4 million tonnes per annum of CO2, which is a lot, is a short way of putting that. They ended up with a 2-year delay at startup because of a corrosion risk in the pipeline. They ended up venting CO2 for 2 years, so at least 8 million tonnes. I can tell you that the real number is significantly higher than that, because even after the 2-year delay, they've had operational issues. And so that number is significantly more than 10 million tonnes of CO2 that have gone into the atmosphere. And the costs, there are fines, and obviously they've had to replace a lot of equipment. So it's certainly in the hundreds of millions of dollars in terms of what this failure has cost them. And fundamentally, this failure came down to real basic stuff from an engineering point of view, and that is understanding the thermodynamics of CO2 and understanding the corrosion risk of CO2. And that's what I'm going to be talking about. This is a technical review for engineers, and so I'm going to be talking technical, and I'm going to be bringing up phase envelopes and all that sort of good stuff. But fundamentally, we want to learn from these mistakes. I'd like to think that this is the sort of mistake that will only happen once, and the best way to make sure that it's a mistake that only happens once is by sharing this information. So this is the Gorgon project. This is in the northwest of Western Australia. I'm actually from the southwest of Western Australia, which is where Perth is. This area here it's just desert. It's the Australian Sahara. There is nothing here. It's incredibly geologically ancient. There are no fault lines nearby. This is land which, from a geological sense, is essentially untouched for millions of years. And what we have is 2 gas condensate fields, the Gorgon field and the Jansz Io field. The Gorgon field, which looks smaller, is the bigger of the 2 in shallower water, and the Jansz Io field is just off the continental shelf in the sort of water depth which is seems quite deep if you're from Australia, but doesn't seem quite deep at all if you're from Brazil. The Gorgon plant site is on Barrow Island, which is offshore. Barrow Island, despite being a very barren island, is an area of ecological interest because it has not been connected to mainland Australia for an awfully long time, which means it does have in its own way a unique ecosystem. When Gorgon were given the rights to build an LNG plant on Barrow Island, as part of the deal, they were told that they had to dispose of the CO2. Both Jansz and Gorgon produce a lot of CO2 naturally in the reservoir. And so, up to, sort of 20 to 40%, depending on the well. So it is a high CO2 field. And as part of the deal to build the plant, they were said that you'll have to dispose of it via CCS, which is why it's where all of the CO2 is coming from. 4 MTPA is a lot of CO2, and indeed there's a lot of CO2 in the gas. This is what it looks like. This is just Google Maps, and as you can see, it is not green. This is desert. Each of one of those little dots there, it looks like a town, but in most cases it's either a crossroads, an iron ore plant, or a house. Just one. This is a big area with nothing in it. I can tell you, let me bring up my little laser pointer here. This area here, called Exmouth, this is actually a really, really nice part of the world. If you ever get the opportunity to visit this part of the world, I totally recommend visiting it. But I can also tell you it's an awfully, awfully long way from anywhere else in the world. If you're in Perth, you can't get to another city without flying for at least 4 hours. And Exmouth is about a 12 or 13 hour drive from Perth. So if you've got that sort of time spare, then maybe it's a place you might go exploring, but I'll forgive you if you don't book tickets to go tomorrow. This is Barrow Island, and as you can see, it really is desert. There are no features there at all. There are no trees or shrubs above knee height. It is very dry and very hot. You can see the slight red color of the soil, and that comes, it's quite naturally high in iron ore, and in fact there's a lot of iron ore that is mined in this part of Australia. What you can see, I'll bring up my little laser pointer again and show you some features here. So in the background, this jetty here, this is where the LNG ships come to load and offload, and it's also where the pipelines come on shore from Gorgon and Jansz. You can see the LNG storage vessels there in the background, the little bulbous tops. This facility here, this is the LNG plant itself. And this over here on the right in the foreground, this is the carbon capture system. So the gas comes in onshore, it gets piped to the carbon capture system where the CO2 is removed. The gas then goes into the LNG plant to be refrigerated. And the CO2, this pipeline here, you can see some little expansion loops. This is the CO2 export pipeline going out to the injection wells. On Barrow Island, it's actually, it's dotted with oil wells. It's actually where the Australian oil and gas industry started. There are shallow oil wells producing very small amounts of oil, but it's still easy enough and cheap to be valuable. And as far as I know, they're still churning away, producing a few barrels a day, which is picked up by a truck with a little vessel on the back. So there is a good 60 years or so of oil production in the area. The CO2 is actually injected onshore as well, so there's nothing offshore about this facility. The CO2 comes out at the CO2 removal plant, and then it's injected just a few hundred meters away. So this is a schematic of exactly the same place. So looking at my laser pointer again, this is the jetty that we could see in the background. These three blue squares, 1, 2, 3, these are the LNG trains. There are 3 LNG trains. And this green line going out to the yellow well pads, this is the CO2 export pipeline. And you can see we've got 9, the yellow circles are the injection wells. So there are 9 CO2 injection wells. The CO2 is being injected into a saline aquifer, which is actually a long way below the oil wells on Barrow Island. And because the aquifer volume is quite small, they produce, they remove water from the aquifer to allow the CO2 to displace it. And then that water is then injected back into the depleted oil reservoirs. And so there might be a little EOR benefit from this as well, but nothing significant. The system is as simple as it gets. We've got an amine unit, which removes the CO2 from the hydrocarbons. We've got a TEG, so a glycol unit to dehydrate the CO2. We've then got a compressor, which puts the CO2 into the dense phase. And dense phase just means liquid. People use the phrase dense phase in CCS for reasons I don't really understand, but if that's what people say, then I'm happy to say it as well. And there are no significant impurities other than water. Now, I can tell you that there is only one route to have rapid corrosion in a CO2 system, and that route is if you have free water. If you have water in a carbon steel pipeline, the CO2 dissolves in the water, which produces carbonic acid, and carbonic acid is very aggressively corrosive against carbon steel. And so when we say Gorgon had an issue with corrosion, that means that they had an issue with water. And you might be asking yourself, how on earth did they have an issue with water when the water content after dehydration is just 50 ppm, which is really low? And if you ask yourself that question, well, you'd be asking the right question, because this, I promise you a phase envelope. Here it is. Oh, here's one of them. There's more, don't worry. So you can see, just to run through this, I spend my life looking at these things, but I appreciate not everyone does. This is temperature on the x-axis. This is pressure on the y-axis. The carbon dioxide is the red line. So down here below the red, the carbon dioxide is a gas. Above it, it's a liquid or in the dense phase. This green line, this is the water dew point. So on the right-hand side, there is no free water, which means corrosion cannot happen. And on the left-hand side, there is free water, which means you will get rapid corrosion. And as you can see, this is where they're operating. These are the conditions. It's pretty hot, so between about 20 and 50 degrees, this is the desert. They have literally got between their minimum operating temperature and the water dew point a margin of 100 degrees. And this is where you're going. With a margin of 100 degrees, how on earth did they get water in their system? Good question. In fact, it gets worse. Is that even upstream of the dehydration, so if we don't dehydrate the system at all, you're still operating in the dry range. So we've estimated that the water content is about 2,000 ppm before dehydration. And as you can see, there's still a margin of about 15 degrees between the operating conditions and the point at which you can get free water. And so what did they do? How did they end up with free water? And the answer is they looked at a chart something like this and they went, even though the system is designed, it's been through the HAZOP, it's been largely built, but they had what they call value engineering, where the key people on the project, they get together and they look for last minute savings. And they said, let's not put in dehydration. I don't think we need it. It looks like the CO2 coming out of our amine unit is dry enough. And if we don't have free water, then we don't have a corrosion problem. Now, the engineers that I've spoken to, and I've spoken to quite a few of them who have worked on the project, the information that I'm presenting you is a mix of information that's already in the public domain and information that's been shared to me in interviews, which is why I'm allowed to share it with you now, because Chevron have never actually shared this information themselves. But there's no, I'm not giving you anything confidential. But I can tell you that every engineer that I've spoken to has said, look, we didn't think this was a good idea. But then when you ask further questions, it becomes clear that the engineers were not able to explain why they felt that taking out the dehydration was a bad idea. And ultimately they were ignored. And so the management team and the lead engineers said, we can remove the dehydration unit. And they would have saved themselves, maybe $5 million, maybe 10, something like that. So a significant amount of money, but nothing compared to what this decision ended up costing them. So what happened? Well, they started up the system. And they started up the system. The first thing they do is they bring in gas from the field. And they put that gas into the CO2 capture system. And then they commission the CO2 capture. And when the CO2 capture is commissioned and they're producing CO2, they then fill up the CO2 system with the CO2 gas, and then they go and commission their compressors. And what this means is that they have now just filled their system with CO2 gas during commissioning, which is right here in this range, right in the area where we get condensation. What's happening here is that when the CO2 is a gas, it's non-polar. But CO2 is a liquid, it is very slightly polar, which means CO2 liquid is much more effective at dissolving polar impurities like water than the gas is. And so even though the liquid would be dry, the dense phase would be dry, the gas phase is not. And so during commissioning, they introduced wet gas into their system. Well, they didn't do it because the operations team, not the engineering team, identified this issue a few weeks before startup. Our estimate is that if they had introduced this gas into their system, they would have had corrosion rate in excess of 100 millimeters per year. That's 10 centimeters per year. Their planned corrosion rate was less than 0.1 millimeters in 25 years of operation. And the lesson here is that CCS is new, and that means that we need to be careful and creative about our engineering, because the people that design CCS systems, they either come from the oil and gas industry or they come from the gas transmission industry, which here in the US they call midstream. CCS is neither of these things, it's something different. And because it's something different, it means that there are these unknowns. And I want to talk about some of these unknowns and what this means, what we can learn from Gorgon and how we can apply this into design of systems in the future. The first is, here's something that doesn't happen in the oil and gas industry. CO2 comes with impurities. I've listed the common impurities there on the right. And these impurities can react with one another. Chemical reactions can take place. So this has been proven in the lab in Norway. Us here at PACE, we've worked with Oxford University in the UK, and we've come up with a comprehensive list of all possible or plausible reactions. And then the outcome of our desktop research has been validated experimentally by other people in a paper, which I've seen but hasn't been published yet, but that's also coming from the IFE in Norway. So we can create new impurities. Now, also, impurities that are polar, they interact with other polar impurities, and this includes water, which means that we're sitting here predicting water dew point. The actual aqueous phase dew point, which is the point at which you can get a corrosive liquid, is a different thing from the free water dew point. Now, again, this is something that we predicted, and this led to a design change on projects, and I'll show you on the next slide what that looks like. This has then gone and been demonstrated experimentally, and we've seen some data from Shell in the Netherlands, which they also haven't published because that might be useful to people. And we're currently working on improving those predictions, because this is the sort of thing that we come across with CCS. It's new. And because it's new, we're having to discover new things that just don't happen in the industries that we come from, the industries where we have experience. And then finally, this aqueous phase can be corrosive. So again, this has been demonstrated in the laboratory, and I've got some exciting pictures to show you what that looks like. And at PACE, we've got a joint industry project where we're developing improved predictions so we can understand what's going on with these aqueous phases, including the products of chemical reactions. This is the outcome of that work that we've done. These are the chemical reactions that we've identified. And if you take a look towards the middle of that list, you'll see nitric acid, sulfurous acid, and sulfuric acid. These are not things that you want in a pipeline. The pictures that you see below, which starts off with completely clean carbon steel and ends up with some sort of brown dust. This is measured in the laboratory. This is the IFE's work. This is published in one of their papers. The difference from left to right is 20 days. That is rapid, aggressive corrosion. Now, this happened at normal pipeline operating conditions, so ambient temperatures, about 100 bar. The composition has over 99% CO2. And the main impurities are NOx, in particular NO2, and water, but they're at low levels at less than 100 ppm. What's happened here is that they've had this reaction here, NOx and hydrogen reacting in a CO2 medium, creating nitric acid. And what we're seeing here is chemical reaction creates nitric acid, the nitric acid corrodes the carbon steel. That's not the only risk. Glycol, which is we use for dehydration and is actually normally thought of as being a corrosion inhibitor, can induce a corrosion risk. I mentioned these aqueous phases. So this is, again, from a real project, this one. This is our phase envelope again. So this is the CO2 line, gas down here, liquid up here. In blue, this is the water dew point. As you can see, temperatures well below freezing. But you add a tiny bit of glycol, and this is just one little droplet carrying over from a glycol unit. And glycol is hygroscopic, which means that even though the water content in the bulk stream is very low, a droplet of glycol will draw water out of the non-polar CO2 gas into the polar glycol. And this dew point is now at or above ambient conditions, and this is a corrosive liquid, and it is one that you will not see unless you consider the impact and the thermodynamics of these very, very small quantity polar impurities. Now, this is a really different issue for corrosion engineers, if there are any here listening in, because typically a corrosion engineer won't be too worried about transient operating phases like commissioning, and they won't be too worried about tiny impurities in, sort of the droplet range, because we think about corrosion as being something which happens cumulatively. It happens slowly over a long period of time. On CCS, that's not the case. It can happen very rapidly, and the presence of certain impurities can induce a corrosive phase. Another example is methanol. So this is some work, again, that we've done at PACE. And what we can see here is we've looked at, if we've got methanol in a system, how much water in ppm do we need before we start seeing liquid condensing. So this is in a specific project. And what we can see here is we can see liquid condensing at around about 80 ppm. Now, if you are only looking at pure water without considering the very small amounts of methanol that are in this system, you would have expected the dew point to be about 250 ppm. And so we're able to demonstrate with a bit of thermodynamics knowledge and a bit of clever data analysis that what we have here is a corrosion risk which comes about because of the presence of another minor polar impurity. And you can see that I've introduced three things all on the same theme, just looking at corrosion with water, and we've got corrosion with water during transient modes of operation, like commissioning. We've got corrosion induced following chemical reactions that take place in a pipeline, leading to rapid corrosion. We've got corrosion induced because of glycol carryover from a dehydration unit, and we've got corrosion induced by methanol, which is a gas which interacts with the water to introduce a corrosion risk that would not be there otherwise. All of these are really important to CCS, and all of these are issues that wouldn't normally come about in an oil and gas or a midstream system. And this is where we really need our creative engineering. Now, the solution here is, this is the approach that we at PACE like to take. This is an idea called the Johari window. It actually comes from behavioral psychology, and it's a useful tool that gets used to try and understand ourselves. So I'm sitting here talking to you. I'm the only person that's inside my head. Everyone else participating in this can look at me and sees me from the outside, which means that I'm the only person here that can't see what it's like to watch me do my thing. I can't watch myself. I can't hear myself. I can't tell really how this comes across. I'm just doing my best, but I'm at a disadvantage because I'm here inside my head. Every single one of you has the same issue in that you are the only person that lives inside your head. Everyone else that you interact with sees you from a completely different perspective. And what this means is that, oh, look at this. Speaking of, I said that people can't see inside your head. Someone has just brought me a beer. How about that? Outstanding. Perfect. I couldn't be happier. Where was I? And what this is so basically it means that there are things in your head which are known to you and known to others. And so that's open knowledge. Now, the things that are known to me, because I'm inside my head, which are not known to you, and these things are hidden to you. But then because I have a different perspective, there are things about myself that I don't know, but you do know. And we'll all have a relative somewhere, a crazy uncle, someone who acts inappropriately in a social space. But you'll know that if you ever bring it to their attention, that they'll deny completely that they're doing something wrong. They've got a blind spot. The psychological term is called anosognosia, and it means to not know, to be unable to know. The skills that someone uses to decide how to behave are the same skills that they use to decide whether or not they're behaving accurately. They're the same skills, and that's how this blind spot comes about. Now, this is useful in engineering because between me and between everyone here, we have an awful lot of experience. Now, there are things that I know, and there are things that you know. And for some of you, in fact, I dare say most of you, if not everyone, I've said things that you already knew. And that's open knowledge. I've got no idea whether you know it or not, but by sharing information, the worst thing that's going to happen is that you get bored. But hopefully, there are things which are known to me which you didn't know. And so by me sharing this information, it's taking this out of this hidden area and bringing it into open knowledge. And similarly, if we are working together, when I'm working with someone who has a different skill set, they have knowledge that I don't do. And they can take information which is unknown to me, which is in my blind spot. And by telling me about it, they can bring this into open knowledge as well. So it becomes shared knowledge. Now, the goal of an engineering team is to bring as much of that combined knowledge and make it open. To take it out of those two areas, the blind spot and the hidden area, and make it open knowledge. And that's why the best engineers are the best communicators, because the best communicators, they share information. It's not about being the smartest person. It's about being the best person to work with. It's always the best communicators. The challenge is this fourth square, this tricky one, the things that I don't know and the things that you don't know. These are the unknown unknowns. These exist in life and they exist in every engineering project. These are the things that surprise you, the things that you can't predict. Now, if it's I don't know it and you don't know it, how are we going to bring this in? Because CCS is a new industry. We're coming across new problems all the time. And the answer to that is what we call consequence-based risk analysis. By looking at rather than starting with our knowledge and going, where are the risks? I'll go, hey, if we've got glycol for dehydration, that might introduce a corrosion risk into our downstream gas pipeline. That's known, and then we can start with the risk, and then we can go, okay, how do we engineer around that? The way to deal with the risks we don't know about is you start with the consequences. And if you're on the Gorgon project, you could start with, well, what are the things we really don't want to go wrong? Now, on that list would absolutely be catastrophic corrosion. And then you work backwards. You go, right, catastrophic corrosion, consequence-based, consequence first. How did we get there? And then it's like, well, there's only one way to get catastrophic corrosion. You've got water in your system somehow. Right. How did we get water in our system? Oh, our gas isn't dehydrated. And then think about the conditions where that happened. And with that process, it's quite straightforward to go, oh, we have got gas in our system during commissioning. that introduces a corrosion risk. Maybe we shouldn't remove our dehydration after all. And so this approach, this consequence-based risk analysis, we think is critical for CCS projects because it brings those unknown unknowns into the light. And I can tell you, we're a CCS company. I'm on the ISO committee, which is responsible for writing standards. We've worked on more than 70 projects, and we come across new things every day. There are things that I've come across today, which is information that we didn't know. And we've done that through communication. We do it on all of our projects when we work with our clients, when we work with other experts, and we share information and we sit around and we ask one another questions. And through asking those questions, we sometimes discover things that we didn't know. And that's absolutely critical. There are a lot of CCS projects out there. There is nobody with a great deal of experience. I mentioned, here I am giving you a presentation, an Australian living in London from Houston who's on the ISO committee for writing standards. I reckon I've got 4, maybe 5 years of experience. In the oil and gas terms, that's nothing. I'm basically a junior. But the fact is that there just aren't people more experienced because CCS is so new. We're all starting from a very low experience base. And that means that we really need to communicate. We really need to think hard about the risk that we're introducing. And thank you. That's it from me. I hope that was useful, from a technical side and from a management side. And now I'll hand back. I can't remember if it's Pierre or Sergio that's doing the questions. But I'd be happy to answer any questions. There you are, Pierre. It's you.
I am with you, Matt.
I'm not breaking any rules by having a beer, am I?
Absolutely. Get started. So thanks for the excellent presentation. I hope it wasn't too technical for some of the audience. I certainly loved some of the details that you brought forward, and it actually reminded me if some of the audience ever have the chance to go to the Science Museum in London, please go to the Energy Hall, and you will see that the age of steam also took a lot of trial and error and a lot of explosions until finally engineers got it right. And I certainly get the impression, based on what you mentioned, Matt, that we are still in the infancy. So there's a lot we need to learn, and we can go about with trial and error, or maybe try to use that novel approach, which I had not heard of before, the consequence-based risk assessment, which I think is probably good to understand what the consequences could be and put sufficient preparation as much as we can into trying to reduce the uncertainty. Before we start taking questions from, and there's already been a few, I can definitely see the interest in CCS becoming a collaborative effort, so collaboration theme, generally speaking, considering it's part of the Sustainable Development Objectives. If we want to continue on the trying to limit climate change, we need to deliver CO2 capture. And to do that, forget the competitive advantage, and let's bring that knowledge, all the lessons from the trial and error and the various workflows together and share the information. That's what science and engineering is about. And you make a discovery somewhere else, there's another discovery, you can discuss, share, everybody's smarter with that. So definitely I hope there will be it'll be the way the industry continues to go.
Great, Pierre. Great comments on that. Matt, thank you for the great presentation. It's very illustrative, and as you know, CCS and CCUS, it has been an important topic here in Brazil recently at the OTC. Our executive manager on the corporate reservoir engineering area of Petrobras, he made it public that Petrobras is setting a foot at CCS, CCUS projects. And as you said, and I'm kind of surprised here, CCS is actually pretty different from doing, let's say, gas EOR, right? There are some differences that someone might think, okay, those are small differences, we can handle that, and look what happens, right?
Yeah.
So go ahead.
And this is Chevron. This is not a, you know, a mom and pop business. They have really good engineers, and yet they learned. They had to learn the hard way.
Yeah.
And to start with our questions, you've showed us some thermodynamic analysis, and it was pretty interesting to see how the decision was taken, having some, let's see, data. It was a decision based on data and experimental data, but the unexpected happened, right? We had a question from the audience that asked, hold on a second. The question was related to the phase diagrams that you've showed here. If those phase diagrams, they were just fitted to experimental data, and what kind of phase behavior data CCS industry needs. And I'm gonna add one little aspect to that question, that is, let's talk a little bit about chemical reactions also. We've mentioned that in the presentation. So thermodynamic and chemical reactions. What do we need in order to be prepared for a CCS project?
The thermodynamic question is a terrific one, and a really important one with CCS. It's only been relatively recently, thanks Raphael for the question, no one's really cared about CO2 with impurities until very recently, which means there's very, very little data out there. Now we have, a few years ago, we got two interns, so an engineer and a mathematician, and gave them the worst summer job of all time, which was, we said, go and find every thermodynamic paper with the word CO2 into it, read it, and tell us if you find anything interesting. So they spent 3 months doing that. They both still work with us, so I don't know quite understand why, but they've chosen to. Their jobs are a bit more interesting now. And the answer is, there is some information out there, but there's not much. The equations of state that we have, that we use in the oil and gas industry, are not really fit for purpose for CO2. But it's obviously going to be a long time until there is sufficient lab data for better equations of state to be ready. It's certainly a few years away. So for now, the approach that we take is we use, depending on what properties we're interested in, if we're looking to look at the behavior of CO2 with light components like hydrogen, then we'll tend to use the Gorgon 2008 equation of state. And we've got, we modify the departure parameters to match the laboratory data that we have as closely as possible. The other thing that we do is we use the CPA equation of state, and that's the one we use the most, because CPA is it's got the cross-associating parameters, which are good for taking into account polarity. And so those are the ones that we use to predict the aqueous phase dew points that you saw. Those were predictions, but there have been, I've seen some data from Shell that matches them in the lab quite well, and we're actually producing some more data ourselves. Now, there are papers available. In fact, we've written one, which I'd be happy to share. If you just drop me an email or get in contact with anyone at SPE, they'll pass it on. And I'd be happy to share the paper where we lay out our rationale for selecting an equation of state and the tuning parameters that we use to match the data as closely as possible. And of course, we're happy to share the source data as well. There's certainly plenty of work that needs to be done on the thermodynamics and on the chemical reactions. The chemical reactions work, it's been shown that some chemical reactions will take place, and we've done work to come up with a long list of chemical reactions that might take place. But as of yet, no one has done work in the lab to understand which of those ones that might take place actually will in reality. In some cases, it's theory. You know, the people at Oxford University are very smart when it comes to taking a reasonable conservative guess as to whether a chemical reaction will be spontaneous. But because we're talking about relatively low, sort of ppm level impurities in a CO2 medium, it might be that a chemical reaction takes place, but it takes a year or doesn't happen at ambient temperatures or whatever it happens to be. So there is plenty of lab work to be done there as well.
Great, thank you. Pierre, you can get the next question.
Yeah, so I have one, and we'll go very briefly on it, Matt. But considering that the wells themselves would have become an integral part of that project, were you also involved in the survivability of the wells themselves? Were they delivered specifically for that project, considering they would also be exposed to the contaminants and the CO2?
Yeah, we see, so most projects are drilling their own wells and putting in tubing, but we do see some projects that are reusing tubing from production wells. The most vulnerable part of the well, there are a few things to think about, but it's usually the cement sheath is the area of interest, because that creates a route from the reservoir back up to the surface. So if that fails, the whole thing fails. That's, like loss of reservoir integrity is one of those big consequency risks that we care about. And so the cement sheath is usually the thing that people are most concerned about. The other well design, there are some interesting things going on in the well, and I could talk for another 45 minutes about those very comfortably. But I won't do that, except to say that, there are some interesting things to think about there, but they have engineering solutions, and ultimately it's not a massive game changer.
Okay, there's been a question from the audience, which I think ties in really nicely with what has been discussed previously. And I'll proceed that with a comment from my part, just to make sure I understand what you have, described basically. But so we can expect to see some compositional variations along the lines, depending on the topology and where they are, and the tiny variations of temperature, right? Which will make the prediction of future chemical reactions extremely complicated.
The good news is that at the moment, at least, CCS pipelines are designed to operate only in gas or only in the liquid phase, which means that you won't see compositional variance because you don't have two phases. You do see compositional change because the CO2 is coming usually from industrial sources, and different industries have different impurities that come along with them. If you're capturing CO2 from a cement plant, it's different than the CO2 you're capturing from a fertilizer plant.
And so the question from somebody in the audience was, is there a magical inhibitor we could use, something we add on purpose to try to address those variations in composition?
Yeah, I can see the questions from Bruno and from Lewis about inhibitors. The answer is that if you treat CO2 well, keep it dry and prevent chemical reactions, and this is possible to do without spending too much money, then CO2 is a very, very benign fluid. We only flow it in single phase, and what that means is that there is never a continuous corrosive phase. Just like a sales gas pipeline, or LNG storage, you make sure that the corrosive fluid can never get in there, which means that there's no need for corrosion inhibitors whatsoever. The risk of corrosion almost always comes from a condensing liquid, which makes it analogous to top-of-line corrosion, which, as we know, is something that we can't inhibit against. And so I have never seen a CCS project which is assuming that corrosion can take place and they're inhibiting it with chemicals. Every CCS project that we've worked on has had the philosophy where they operate entirely dry, thereby protecting the system from corrosion and removing the need for inhibitors entirely.
Even for transient phases or project
even
phases?
For transient phases, yeah.
Okay.
Great. Matt, let me ask you a quick question. We're talking about CCS. I've been using to talk about the CCUS. If you can quickly comment on the U on CCUS and what you've been seeing all around the world on that.
Yeah, there are a few uses for CO2. So you can make methanol from CO2. You can make xylene for CO2. Methanol and xylene are both very useful chemicals. And there are other uses as well. It can be used in greenhouses or for, dry ice for food and things like that. And it's used to make urea as well, which is fertilizer. To reach net zero, the best estimates that we've got from the IPCC and from analyst companies like Wood Mackenzie is that by 2050 we need something like 8,000 million tons per year of CO2 to be disposed of. The amount of CO2 that is useful is a tiny, insignificant fraction of that. It's very difficult to design a CCS project and then try and find a way to sell the CO2, because in this world we have an excess of CO2. It's a waste product. It's a bit like having wastewater and then thinking, oh, maybe we'll find someone who wants this water and we can make a bit of money out of it. There are uses for CO2, but there are very, very few CCS projects that have any valuable use for the CO2. It's a waste product. We need to get rid of it, and there's no magic process which is going to take all of the CO2 that we're producing in the world and turn it into something that's useful.
Great, Matt. Thank you very much. Do you have any more questions, Pierre? What?
Well, I think we're getting close to the closing of the event, but maybe I'll tie it back to Brazil. I totally see the industry being extremely enthused about CCS projects for some reasons, including the potential to repurpose installations. If you had a few recommendations for project owners in Brazil who would like to start something, whether offshore or onshore in Brazil, what would those recommendations be, Matt?
Yeah, so it costs money, and so fundamentally there needs to be a reason to spend that money. One reason might be that it becomes there's a commercial case. In the US, there are tax credits available. In the EU, there is a carbon tax, and indeed they're putting on tariffs, so there might be a strategic reason as well. But regardless, the goal is going to be to make a project as cheap as possible. And that means that you need the cheapest source of CO2 and you need the cheapest store. The cheapest source of CO2 is going to be pre-combustion CO2, which is almost certainly a fertilizer plant or an ammonia plant. They should be the first sources because the CO2 at the point of capture is quite high pressure, which makes the capture units much lower cost than they are for post-combustion CO2, like a power plant. And then when it comes to the store, different things happen around the world. The cheapest way to a store is almost always injection onshore. So an onshore injection well into a saline aquifer. That may or may not be geologically possible. I don't know enough about the geology around Brazil. The worst case scenario is, I regret to say, injection into a depleted hydrocarbon reservoir in deep water, which I suspect that you've got you've got plenty of those. The third one is shipping, which means that you export to a ship and then that ship takes it to a store which is cheaper. Places like Trinidad are obvious locations where the water is relatively shallow. There's good geology that might make a suitable disposal point. But fundamentally, it comes down, a CCS project is connecting a source of CO2 to a store of CO2. The most expensive part of that chain will be the capture. And so the first step is what's the cheapest capture? And then the second question is what's the cheapest store? Once you've identified those two things, and hopefully they're right next to one another, although that's quite rare, then you can start thinking about how you go about designing the thing that connects the two.
Very good.
Great. So, Matt, thank you very much. Pierre, thank you very much. I think we got to the end of this wonderful presentation and discussion. And I want to end this repeating what Pierre just talked right after your presentation. CCS, CCUS, it's a challenge. It's important. It's an important drive for the transition energy for us to clean, to provide a cleaner environment for our world. And the only way we have to succeed in that direction is through collaboration, right? So our industry is truly important on that matter. Collaboration is truly important in between each company, and the best way to do it is through SPE, right? Just the same way we're doing here right now. Okay. So thank you very much, Matt. I truly appreciate. Thank you, Pierre, so much for finding Matt and bringing him to that presentation to share his knowledge with us. And I'm gonna switch to Portuguese now, so I can have our last warnings after the presentation. Okay, thank you.
Thanks, Sergio. Thanks, Pierre.
Enjoy your
Thanks
beer.
to Eduardo
Enjoy your
as well.
beer, Matt. Yeah.
Enjoy your beer. Yeah, that's right. Muito bem, pessoal. Muito obrigado a todos aí da audiência, né? Todo mundo que está aqui, né, compartilhando com a gente nessa apresentação, esse conhecimento. Como eu falei, né, a importância, né, da gente estar colaborando e discutindo nesses tópicos importantes e atuais, né, é muito grande, e a maneira que a gente tem de fazer é através do SPE, né? O SPE, essa nossa Sociedade de Engenharia de Petróleo, ela provê, né, a oportunidade da gente estar em contato com diversos profissionais, diversas empresas, né, e com um nível de conhecimento, né, muito grande. Tá? Então, eu convido todos vocês a entrarem no site do SPE e se cadastrarem, né, e se virarem membros, né, do SPE, para que vocês possam estar cada vez mais perto, né, dessa comunidade, né, que é uma comunidade muito grande, que favorece muito, né, o trabalho de todos nós. Tá bom? Para fechar, eu queria falar dos nossos patrocinadores, né? Na verdade, do nosso patrocinador Gold, né, que é a empresa Enalta. Agradecer, né, o suporte, né, técnico e financeiro para que a gente possa estar realizando e compartilhando, né, esse conhecimento, né, com todos os membros e não membros aqui do SPE. Tá? Mais uma vez agradeço a todos vocês, né, pelo tempo, pela presença, tá? E convido vocês a entrar no nosso site. Qualquer dúvida ou desejo de trabalhar como voluntário, por favor, entre em contato, tá? A gente está aqui à disposição. Uma boa noite a todos e até a próxima Tech Tuesday. Thank you very much, Matt. Thank you, Pierre.